This idea is a little bit of attack on each you need to know our book doesn't go. So it's kind of outside the book, but definitely something that goes with series. So this, whether you know it or not, is a big one. This series that we typically call 1 over 1 minus x is huge, and it leads to lots of series. And we touched on this a little, but I want you to understand there are at least 4 different ways I can get a series for whatever it might be, if it's in that form. What's one way? What? Yeah, integrating? That's the starting point. Oh, no. Let's go with, what's the first thing you did? When you did a series, the first thing you did is you took derivatives and you built. Yeah? Are you with me at all? This is not going well already.
I was saying, you take the
Oh, you wouldn't do
natural log.
Yeah, but you would have to know natural log to get there, and you don't usually know natural log to get there. But you're right, I see. You can take a derivative. So you could build it, yeah? From scratch. Any other things you could think of? I have 4 for Pete's sake. Geometric series. Okay, this is a geometric series because it is of the form a1 over 1 minus r. And because of that, I could say, well, I know then this is like the series a1 plus a1r plus a1r squared, and so on. I could build it through a geometric series, geometric formula approach. That's actually the most applicable, the most useful of all, which we need to practice today.
Oh, you can divide.
You can divide. I could divide 1 minus x into 1, and I could get the series that way, through division. And the last, I'm blanking on the last one. What's the last one?
We barely knew the first one.
No, you didn't know the first three. What's the last one? Oh, come to me. Darn it. Okay. At any rate, the geometric one is the start of the show here today. We have, practiced. You could, actually, sorry. This then, say it's one of these here. We also do by substitution if it's different from 1 over 1 minus x. Now, we've been doing that the last couple of days. For example, if you had 1 over 1 plus x, then you might do it by substitution with what going in for the x? Negative x going in. Okay, now, the geometric idea is especially done a lot in differential equations, so I need you to be familiar with it, but it's just a great idea. So, if you were to write the series for this in a geometric series, use the formula approach, then you first of all need to make it something over 1 minus this. You, in other words, need to make this 1. Now we could do that by factoring out a4. Inside then, the 4 becomes a 1, and the x becomes a 1/4 x, or x over 4. Do you agree that if I distributed that back, it is right back to where it started? Are you with me?
Yes.
Okay, typically then, you would lump that number in with the numerator and call that 1/4, 1 minus x to the 4th. That then said, this is the geometric series with an a1 of 1/4 and a common ratio of x over 4. And so by that token, a1 is 1/4. Each time I get a new term in the series, I get it by multiplying by the common ratio. So when I multiply 1/4 by x over 4, multiplied by x over 4, I get x over 4 squared, or 16. And then if I multiply by x over 4 again, I get x squared over 4 cubed, and x cubed over 4 to the 4th, and so on until let's talk general. Now you could look at the pattern and build it that way, or you could say, what did I do each time? Well, I started at 1/4 and multiplied it by x over 4 some number of times. Wait. All right then. Now then, if you were to use that same approach, try this guy. Again, the first thing you're going to want to do is try and make it like a geometric series. So something like, I might start by putting the constant first in the denominator. And then what should I do? Make it 1. Make it 1. Okay, so how do I make that 1? With 2/3. Actually, I'll do it slowly. Factor out a 3, leaving me with 1 plus x. I over 3, right, thank you. X over 3, good call. So that then is 2/3 if I bring that up and total it up with the 2. And then the bottom I really need to write as 1 minus something. And 1 minus negative x over 3. That means then that A1 is 2/3 and the common ratio is negative x over 3. So if I start with the first term of 2/3, and every time I get a new term, I'm going to multiply by negative x over 3. So what is term 2? Two x over 9, or over 3 squared. And if you multiply by negative x over 3 again, I'm going to change signs, and that'll be 2x squared over 3 cubed, and then minus cubed over 3 to the 4th. Let's go to the general term. The general term came from starting with 2/3 and multiplying by the common ratio, negative x over 3, some number of times. Are you with me? Okay, try these bad boys. Do you feel like you know enough to try this on your own? Okay. I don't like it. How we doing, people? Okay. What'd you get for a general? Something along the lines of 2 over x. I might have to clean this up. 2 over x squared is what I started with, and I multiplied by 3x n times. That's not a great general term, but there's 2 different x's. So let's clean up the x's, shall we? let's call this 2 times 3 to the n is cool. But what about the x's? X to the what? 2 minus n or n minus 2? N minus 2. Yeah. Okay. You follow? Okay, try the last one. Oops, that should be 1/8, shouldn't it? I kind of have a rough draft of my general term, but I'm going to clean it up. Let's see if we get the same thing. So, the x and the negative are kind of two separate bags, yeah? So I'm going to separate the negative. -1 to the what? To the n. The 3 is always there. 8 is to the what? 8 to the n. 8 in the denominator. 8 to what power? N plus 1. And x to the n plus 1. I guess I could call that x over 8 all to the n plus 1. But that is fine. All right, are you with me? This idea of geometric is useful in a lot of fields. If you see that fraction kind of form, then think about it this way. I forgot to throw on one that tends to, there's an AP problem that always gets students. Imagine if you saw something like this. Find the infinite sum. 3 times 1/2 over 8 minus 3 times 1/2 squared over 8 squared plus 3 times 1/2 cubed over 8 cubed. Exactly. Now, if you try and look at this in a sum way, you're sunk, because that's going to be really hard, especially without a calculator. But if you look at this the right way, this is easy. You'd say this is equal to the series for what? It should look familiar. This looks like the series we just did. 3x over x plus 8 with an x of 1/2. Therefore, it's equal to this when x is 1/2. And so it's equal to 3 times 1/2 over 1/2 plus 8, or 3 halves over 17 halves, or 3/17. That thing equals 3/17. Okay, now you're not going to make that connection or make that sum trying to look at it infinitely. You need to make the connection of the jump between geometric and the series. All right, that's the only way you're going to get there. I love substitution, and you could have done this by substitution, but if you only think substitution and not geometrically, you cannot answer the question. Okay? All right then. Speaking of numerical estimates and such, the idea in the book the last really one we have to talk about in series is how can we use a series to estimate an integral that we could not otherwise do? For example, the sine of the square root of x. It has no antiderivative. You cannot find a function that has a derivative with that. There isn't one. And yet, you can still estimate the area under that curve using series if you have a series for this. So, we're going to create a series. First of all, you know sine is what? X cubed minus x cubed over 3 factorial plus fifth over 5 factorial dot 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 dot. Okay? Therefore, sine of root x by substitution is root x minus root x cubed over 3 factorial plus root x to the fifth over 5 factorial, and so on. Now, I'm not going to sweat the general term because they want a numerical estimate. So I'm going to be all focused on just the numerical pieces, not the general. I want to then get a series of, instead of the function, I'm going to use an integral, rather than the integral of the function, I'm going to use an integral of the series. This would be, or can be, approximated by the integral from 0 to 1 of root x minus, let's call it, to use the power rule, let's call it x to the 3 halves over, what, 6, plus x to the 5 halves over, what's 5 factorial, people? 120, and so on. Maybe I'll need to know more, not sure. Now, if I integrate this, then, what's the antiderivative of x to the 1/2? 2/3 x to the 3 halves.
Why did you do 0 to 1?
It should be 0 to 4, sorry. It's 0 to 4, not 0 to 1, my bad. 0 to 4. 2/3 x to the 3 halves minus 2 5 halves times 1/6 plus 2/7 x to the 7 halves times 120th. Maybe we'll need more, don't know. Call it 0 to 4. Are you with me? All right then. Plugging in numbers, I'm looking at 2/3 of 4 to the 3 halves minus, let's call that 1/15 4 to the 5 halves plus 1/420th 4 to the 7 halves, and all that would be minus zeros for all the terms that are going to be put in a 0, yay? All right. So let's get estimates here. What's 4 to the 3 halves? 8, so that's feeling like 16/3. What's 4 to the 5 halves? 32/5. What about 4 to the 7 halves? Did I make a mistake?
Yeah.
Oh, it should be a 15 here. You're right. Thank you. 32/15. Thanks. Okay. 4 to the 7 halves. What's that? 64. 128. 128 over 420. Okay. Now I could keep going, but let's talk the error bound. They said error less than 300ths. Oh my God, this might take a while. Let's go with less than 3/10. No, that's not even 1/3, yeah. Or that's more than 1/3. I think I originally had it going from 0 to 1. That's why I shouldn't have changed that one here. Let's go with less than 1/2. Shall we? Okay. Just to get moving along. Now, this, in order to use error bound, we have to justify it. This is alternating. The terms decrease to 0. So it is true that the difference between the true sum and the error, or the estimate of, now how many terms are we going to use? What's the first term that's less than a half? The third term, do you agree? So as an estimate, we're going to use an S2. S minus S2 will be less than or equal to A3, which is 128 over 420, and that is less than a half, yeah? So our estimate, S2, is 16 thirds minus 32 fifths, 15ths rather, sorry, which is 80 15ths minus 32 15ths. So our estimate is 48 15ths. Or I suppose, 16 fifths. Okay. Wow, you guys are as dead. Do you guys have a paper due today or something?
Tomorrow. Yesterday was due tomorrow.
So why are you tired today?
For standards.
Because you're famished?
In between two due dates.
Oh, sandwich. I thought you said you're famished.
I'm really hungry.
Sure. Okay, the energy in this room is non-existent. What a bunch of stiffs. That's 16. Okay. It makes me want to just throw up my hands and say, whatever, you're not into it. But it's my job, so I'm going to go with it. All right, so here we go. The last test, the binomial series was dreadful, and I entirely expect that I will reassess whether you are any better this time. So that's why I put this into my notes, because I felt like you needed the practice on binomial expansion. So, before you can use a series or get any error term, you need to develop the series for it. I would strongly suggest you don't go with x to the fourth. Instead, go with the series for x plus 1, then substitute in x to the fourth, and then estimate the integral. Okay, so if we use the series for x plus 1, what would be a logical center?
Should we do 1 over x?
1 over x plus 1, thank you, sorry. 1 over x plus 1, or x plus 1 to the negative 1/2. What is a logical center? 0. Yeah, we'll use a center of 0. So, if a center of 0 is used, and what is f at 0? 1. What is f prime at 0? The first derivative at 0 would be negative 1/2, x plus 1 to the negative 3/2, at 0, which is positive negative 1/2. Negative 1/2, then it would be x to the first over 1 factorial. The next derivative, there you go, negative 1/2 times negative 3/2, x to the second over 2 factorial. The third derivative, I'm going to go one more term just in case. What's the next derivative? Negative 1/2, negative 3/2, negative 5/2, x cubed over 3 factorial, and so on. Now then, if I sub in x to the fourth, then 1 over the square root of x to the fourth plus 1 could be approximated by the series 1 minus 1/2 of x to the fourth, minus maybe, or plus rather, 3/8, and instead of x squared, x to the fourth to the second, which is x to the 8th. Then we go to minus, this would be 3 times 2 times 1, so a 3 would go away, so I'm thinking maybe minus 5 over 16, x to the, what? What? 12, yes. Okay, sounds good. So my estimate then of the integral estimate would be the integral of the series 1 minus 1/2 x to the 4th plus 3/8 x to the 8th minus 5/16 x to the 12th, and so on. I don't know how many of those I'll need to get error less than 1/40th. We'll see. Maybe I'll have to go back and do some more. So what's the antiderivative? No C for a definite integral, so don't sweat that. X minus 110 x to the 5th plus an 8. So 3/48, so 3/72 x to the 9th. I don't 12 times 16.
Wait.
160 plus 32, 192 maybe? Oh, 13, darn it. So 13 times 16, where we got the 48, 160, 208 maybe? Okay, we'll see if we need it. All right, if we evaluate that from 0 to 1, then we get something like 1 minus a 10 plus 3/72 minus a bunch of zeros. If we want error less than 1/40th, will that term do it? 3/72, or are we going to need one more? Is 3/72 less than 1/40th? It is not. It's 1/24th, which is not less than 1/40th, so we need one more term. So when you raise this by 1, it is x to the 13th, 16 times 13. Mentally, people?
208.
208, good job. 5 over 208, x to the what? 13th, which at 1 is 5 208. Is that less than 1/40th?
Yes.
Yes, 5 200ths would be 1/40th, so 5 208ths is less. So by alternating series error bound kind of thing, this is an alternating series, alternating terms, limit to 0, they decrease. So the difference between the true infinite sum and how many am I going to use? 3 is less than or equal to A4, which is 5 208ths, which is less than 1/40th. Sum 3, the estimate is whatever that is, 1 minus a 10th plus 1/24th. Just because I want to make you pay for being so terrible, let's figure that out. So that's what, 240 minus 24 plus 10, or 250 minus 224, 226 over 240. Okay, are we cool? Great. This is meant to give you practice on the geometric idea, but quite frankly, can't watch you sit through that and then try to teach differential equation. So on I go to the last question, differential equation. Rarely in high school text, but many times in college text, they use differential equations with series. I would like you to be familiar with it. So you might see a question like this. Say I gave you the basic geometric series 1 over 1 minus x. Find the series for x, y plus y prime minus 1. I suggest you go slowly and build it. So for example, start with the series for y. What is y's series? Given that y is f of x, what's the series for y, or 1 minus x? 1 plus x squared plus, this one you do want the general term, so go there. Okay? To finish that term, you want xy. So what's xy?
Multiply it by x.
Multiply it by x. So it's x plus x squared plus x cubed plus, now I could call the general term x to the n plus 1, but isn't the one before it just also x to the n? You with me? You could call it n plus 1, but you could also call it n because they're both in there. Now, separately, you'll also need y prime. What's the series for y prime? 1 plus 2x plus 3x squared plus the derivative is nx to the n minus 1. What's the one after that? N plus 1 x to the n. Okay, cool. Now, then, if I take the pieces for this and combine them all, xy plus y minus prime minus 1, it would be the series xy, so x plus x squared plus x cubed plus the series for y prime, which is 1 plus 2x plus 3x squared and then subtract a 1 and simplify. So the 1 goes away. That's nice. The 1 is, let's start with the total of the x's. What's the total of the x's? 1x and 2x is 3x. X squared and 3x squared is 4x cubed. X cubed, and what is the x cubed term here, which I didn't show? It's a 4x cubed, so x cubed plus 4x cubed is?
Isn't it 4x squared? Yeah.
4x squared, thank you. Okay, 4x squared. What's the total on the cubes? Go ahead.
In the general term of the y prime,
Yep,
why did you do that second version of that term?
this one?
Yeah.
If I'm going to add like terms, then I need to see the x to the n. So I need that to be the same.
And then why can you have the same general term for the y and the xy and they started with values?
Doesn't matter. What matters is the x to the power, because that's what I'm going to add. Okay, so in terms of the next term, how many x to the thirds? 5x cubes. Generally speaking then, here's the x to the n. Here's the x to the n I'm adding to it. So a total general term of n plus 1x to the n's plus 1x to the n is n plus 2x to the n's. Does that check? Is the coefficient 2 more than the exponent? Yep. 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 Okay, so that is your series. All right, that then you will have a chance at the hardest AP series problem of all, which I intended to put on the text list. All right. Boom! Questions on the homework. Here's the homework.
The division one.
The division one. It really wasn't a division one, though. It was really a multiplication one, though, right?
Oh, yeah. Oh, 1 over 1.
Yeah, it didn't even occur to me. I was starting to divide. I said, wait, 1 second. It's already in the denominator. So, yeah. I intended for it to be division, but I made a bad problem. All right, so this was something like 1 minus x plus x squared through a negative x to the n. So we could also talk a whole another day about 2 ways to go about this. I could imagine going about this 2 different ways because they didn't say the center. Did you do something like factor out the 2 kind of thing? How'd you do with that 2? 3 halves, okay. 3 halves, 1 over 1 minus x over 2, like that? Okay, now really, it is probably, if they say a series, it's probably not okay to have that 3 halves out there. You really need to distribute it into every term. Otherwise, it's not really a series, which is the sum of infinitely many terms. It's a product. And so, you probably need to distribute if you did this. 1 plus x over 2 plus x squared over 4 plus x over 2 quantity to the n, which, if we were to do this in a geometric way, we would be saying a1 is 3 halves, and we're multiplying by x over 2 each time. And so we'd have something like 3x over 4 plus 9x over squared over 8. And we'd say it's something like 3 over 2 times x over 2 to the n, or something like that. Yeah? Okay. Just in case somebody's a creative thinker, and definitely some person, at least the people last year, said, what if I did that? 3 plus 1 plus 1 minus x. That's equivalent. And that is a series, and it would be something like 3 times 1 plus 1 minus x to the first, plus 1 minus x to the second, 1 minus x to the n. And that would not be bad. The difference is the center would be 1, not 0. However, whether you know it or not, you just increase the interval conversion. Well then, how about this? Did you take something like x times the series for 1 minus x, or 1 minus x to the fourth? I hope. So a little substitution, multiplication, make sure maybe something like x plus x to the fifth plus x to the ninth plus x to the 13th, dot, 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 x to the 4n plus 1. And then the important one is 1 minus x squared plus x to the 4th minus x to the 6th, negative x squared to the n. That's important because that is what's going to lead to your next problem, our tangent. Our tangent is the antiderivative of 1 over 1 plus x squared. So it's the antiderivative of the series above. Okay? I can tell you some of your homework for finding the C. Here's a big old stack of homework. And by one, I mean several. Sorry to dump that on you. That's kind of funny. If you don't have the C here, you will be losing at least 1 point, actually 2 points. Okay, you need to show that this is C plus x minus x cubed over 3 plus x to the 5th over 5, dot, 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 negative 1 to the n, x to the 2n plus 1 all over 2n plus 1. Okay, second, most of you would lose points, and I'm talking most of you. Most of you would lose points for the quality with which you find the C. I have no idea what you did. I have no idea what x you used. You just magically all of a sudden have C. That is terrible math. You should say if x, this is arctangent. Most of you don't even know what you're finding, or that it's equivalent to arctangent. You don't even have another side of the equation. You just have some floating series. Okay, this is supposed to be our tangent. If x is 0, then on both sides 0 goes in, not one side, both sides. C plus 0, dot, 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 dot. That's what allows you to say C is 0. And therefore our tangent is what it is. You need to show both sides of the equation. You need to identify what x you used. Otherwise your work is garbage. Okay, boom. Interval of convergence. My interval of convergence was negative 1 to 1 inclusive. Do you agree? I can come back to that.
Is it 1 to 1 inclusive?
Say again? Inclusive, yes. Wait, it's an alternating harmonic both ways. But we can go over that in a second. E to the 2x by substitution is 1 plus 2x plus 2x squared over 2 factorial plus 2x cubed over 3 factorial plus 2x to the n over n factorial. Okay. The multiplication was, and I definitely didn't give you enough room to get many rows to the multiplication done. So I looked something like e to the x is 1 plus x squared over 2 factorial plus x cubed over 3 factorial. And then e to the x again is 1 plus x squared over 2 factorial plus x cubed over 3 factorial. So when I multiply, first time through I multiply 1 by everything. When I multiply 1 by everything, it is 1 plus x squared over 2 factorial plus x cubed over 3 factorial at the top. Now I multiply x by everything. If I multiply x by everything, I'm going to need to shift over a little to line up like terms. So I'm going to get something more like x plus x squared plus x cubed over 2 factorial. If I then multiply x squared over 2 factorial times everything, then it's x squared over 2 factorial plus x cubed over 2 factorial plus x to the 4th over 2 factorial, 2 factorial. I wasn't quite sure if I was going to even see the pattern, quite frankly. 1 plus 2x, that was going nice enough. What's the total here? 1 half x plus x squared plus 1 x squared plus 1 half x squared is 2x squared, yeah? That seems wrong. Yeah, no, that's right. Actually, that makes sense. That would work, right? 4 over 2 is 2x squared, so it's Simon. At that point, then, I started to say, well, you get the idea. I didn't actually start getting common denominators. I trusted that it's working. But obviously, substitution is way better, right? Right. Okay. Here, e to the x sine of x. Hopefully you have something like x plus x squared plus 1/3 x cubed. The x to the 4th term actually went away, yeah? So that was kind of weird, 4th degree, but there wasn't a 4th degree term. Sine of x over 1 minus x, I actually treated this like multiplication, although it felt like division, and that was actually what I intended. It didn't turn out that way. It was actually multiplication. So x plus x squared plus 5, 6 x cubed plus 5, 6 x to the 4th. This, there are a couple different ways of going about this, some easier than others. Some people wrote the series for each of these. That is definitely the long way to go about things. The easier way might be to say, don't know what that is, don't know what that is, don't know what that is, but hey, I recognize this. This is blank to the n over n factorial. That is e to the blank. And what's in the blank? -2. It's e to the -2, and therefore it is b. Okay.
Can we go up a little bit to the left?
Back.
Were we supposed to do division?
Multiplication. Because 1 over 1 minus x is already a fraction, as it is. So multiplication is
Would you
something.
still give me the same answer?
No.
Yeah.
Okay. And last but not least, I have D. We? Okie dokie. Anything else you'd like to talk in more detail about? Yes, ma'am.
Or like, how do you know which?
Oh, good question. This, actually, good point. This is a good question. Do we agree that we, by substitution, we get down to C and D? I didn't do any interval ratio. I didn't do any of that stuff. I just said, you know what? I will be able to distinguish between when x is 1. And so if I use x of 1, then on does x of 1 work? It would be 1 minus 4 plus 16 minus 64. Would that converge? It would not. So 1 is a no. So it must not be an interval. It must be. Okay? That's a good question. That's how I distinguish between them.
Wait, just for, so, just like this, if you divide sine times by 1 minus.
That's correct. Because it's not the difference. That would be, the question is what sine of x times 1 minus x.
Oh, but the I use the series of 1 over 1 minus. Yes, okay.
One question.